It's Paul with the last of the 3 Thanksgiving week videos. This one is on concave functionals, and it will take us up to the point where next Monday we can get to business proving the Fenchel duality theorem and applying it to a variety of fascinating optimization problems. There's no such thing as a concave set, but there is such a thing as a concave functional. And the rule is very simple. A functional is concave if the value at the interpolated point is greater than or equal to the interpolation of the 2 function values. For real valued functions of R, all this means is that the line joining 2 points on the graph always lies below the curve rather than always lying above it. Because we have less than or equal to or greater than or equal to here, a linear functional for which the 2 sides are equal is both concave and convex, and I'm going to use a linear functional as my first example. First, let me give you the definition. This looks an awful lot like the definition of the conjugate convex functional. The only difference is that instead of taking a supremum, I take an infimum. The conjugate domain, D star, is where this infimum exists, and the conjugate functional, G star, is the value of the infimum. So let's try this out, and let's try it out on a functional for which we already know the conjugate convex functional, namely the function is going to be g of x is equal to 0, but with a domain D that only extends from 1 to 2. So we've got an x star in the dual space, and that can be represented by some slope m times x. So what we want to do is graph the conjugate functional g star as a function of m. Okay, what do we have to look for? We have to look for the infimum of the difference between a linear functional and the functional g that we're given. And it's clear that if we're dealing with a positive slope, the infimum is achieved at the left endpoint of the domain. There's the value of the infimum. Another way of calculating exactly the same value is by sliding this line down from above until it just touches the graph of the functional g on the domain, and then the intercept is minus g star of m. In this case, it is equal to minus m, and we figured out that if m is positive, g star is the identity function. G star of m is equal to m. Its graph has slope 1. What happens, on the other hand, if we consider a negative value of m? Well, again, we can take the approach of, let's take a line with negative slope and slide it down until it touches the graph. Here it touches the graph. It touches the graph at 2. And the value of the functional m of x, m times x, with negative m, is fairly far below this graph. How far below is it? It's 2m below. And so we can look here and say negative g star of m, this intercept, is minus 2m, and we conclude that for negative m, g star of m is equal to 2m. Notice it's happened again. One endpoint of the domain has become encoded in the slope of the line up here. The other endpoint has become encoded in the slope of the line down here. So it shouldn't be too much of a surprise that we can recover the original function. Here's how we do it. slide a line of slope x down from above. See where it first touches the graph. Now this will only work if x is between 1 and 2. It touches the graph right here, and that lets us conclude that since the infimum is 0, the value of the conjugate functional is 0, and we have recovered g of x equals 0. If we choose a line whose slope is less than 1 or greater than 2, that line, no matter where we place it, is going to intersect this graph. That means there is no infimum, and that just means that that value of x is not in the domain d star star, so we have reconstructed the domain d as the interval from 1 to 2. By way of comparison, here's a plot of f star for exactly the same function, the same domain. This is convex. This is concave. That's a general rule. The conjugate of a convex functional is convex. That of a concave functional is concave. And furthermore, you can see how to turn this graph into this one. You rotate through 180 degrees, or if you want to put it algebraically, g star of m is minus f star of minus m. Let's do another example. An easy way to create a concave functional is to take a convex functional and slap a minus sign on it. So since we dealt with f of x equals plus x squared, let's deal with g of x equals minus x squared and see what happens. The argument is very, very similar. Now what we do is imagine that we're sliding a line of some slope m down from above to see where it first touches the graph. And if m is positive, we first touch the graph at 0, the left endpoint of the domain D. If, on the other hand, m is very negative, if it is less than minus 2, it first touches the graph here at the right endpoint of the domain. And if m is in between negative 2 and 0, we have an honest-to-goodness elementary calculus problem. We have to find the infimum of mx plus x squared. We do that, of course, by setting the derivative equal to 0. Get m plus 2x equals 0. The solution is x equals minus m over 2. And g star is equal to m times the value of x that we found minus the square of the value of x that we found. Yet again, we get two terms that are very similar, except they've got different coefficients. When I combine them, I get minus m squared over 4. You may remember that with the convex functional x squared, the conjugate functional was plus m squared over 4. If I plot this g star, it is a function whose graph is a straight line up to m equals minus 2. Then it's a parabola, and then it flattens off. Here, by way of comparison, is the f star we computed previously. It is a constant 0 for negative m, then a parabola, and then the straight line m minus 1. And if you compare these two functions, you again see you can convert this graph into that one by rotating through 180 degrees, or again, g star of m equals minus f star of minus m. Now, there are two sorts of concave functionals that figure prominently in the applications that we're going to be doing. And so I want to show you a general rule for calculating a conjugate concave functional. We have to distinguish two cases, and here they are illustrated graphically. I'm interested, as usual, in functions that are powers of a positive number x. In the case where the exponent p is greater than or equal to 1, we have a convex functional. But in the case where p is less than 1, we have a concave functional. Here's the first case. The first case is an exponent p that's in between 0 and 1. An example of this would be the square root of x. And I want to specify my function as alpha over p times x to the p because I did a computation of the conjugate functional that was just as valid for p less than 1 as for p greater than 1. Before actually applying the formula, let's have a look at case 2, another way of getting a concave functional. You can see very clearly, by the way, that the line joining 2 points on one of these graphs lies entirely below the graph. It is a concave functional. I can do this one by taking 1 over p times x to the p, where p is less than 0. And before you say, hey, shouldn't you put a minus sign on it? No, p is a negative number, and 1 over p is a negative number. So an example of a function of this sort would be 1 over negative 2 times x to the minus 2. Now, let's use the formula we proved earlier. If g is alpha over p times x to the p, the conjugate functional is alpha to the 1 minus q times 1 over q times y to the q, where as usual 1 over p plus 1 over q is equal to 1. Only here, p and q are not both greater than 1. Let's see what happens. In case 1, we have an exponent that's in between 0 and 1. So if I take 1 over q, which is 1 minus 1 over p, since p is less than 1, 1 over p will be greater than 1, and this will come out to be less than 0, and q will be less than 0. In other words, if we take the conjugate functional for case 1, we get a conjugate functional that is of the form that we've described as case 2, and concave turned into concave. Does it work the other way around? Sure it does. In case 2, where q is derived from a negative value of p, 1 over q is 1 minus 1 over p. Well, p is negative, 1 over p is negative, this term is positive, and we're going to end up with something that is greater than 1. That means that q is going to be a positive number less than 1. We've got back case 1. And furthermore, because q is in between 0 and 1, alpha to the 1 minus q is going to be still a positive number. Notice in both these cases, alpha raised to the 1 minus q power is going to be a positive number. Here, this exponent is bigger than 1. Here, it's less than 1, but it's still positive. Okay, we are in business. On Monday, I will start out by proving the Fenchel duality theorem, and then we'll spend the rest of Monday and Wednesday doing some applications.